So now we're getting into some pretty complicated problems you can solve with Newton's second law. There are two things that you really need to take away from these examples. One of them we talked about in class. If you have two masses connected together, and you cause one of them to have an acceleration by pulling on it, the other one will have the same acceleration because they're connected. If I take one of the boxes, pull on its string, and it accelerates, the other one's going to come along with it, unless, of course, the string breaks. So unless the string breaks, two connected objects have the same acceleration. Then second, remember, everything for forces and acceleration comes down to Newton's second law. F net equals ma. All right, let's dive into an example. All right, here's our first example. Find the coefficient of kinetic friction, mu k, between the block and the table if the acceleration is 5 meters per second squared once the block is set in motion. Remember I told you to think about what you need to know just before you can answer this question? So if I'm looking for mu k, I'm obviously going to use the equation force of friction equals mu k times the normal force, which means right before I can have mu k, I have to know the normal force and friction. Looking at this problem, the normal force is going to be pretty easy to find. We're talking about this block here. It's the only one that has a normal force, and therefore the only one that can have a coefficient of friction. If we were to look at the up and down forces for this box, that box is not falling down, it's not flying up, therefore its up and down forces are balanced. And so we could write F up equals F down. Its up force is the normal force, its down force is its weight, and looking at that box, if it says 0.5 kilograms, its weight is 5 newtons, therefore the normal force for that box is 5 newtons. So I now have the normal force for the box. I still have to find the force of friction. This problem is talking about acceleration. This problem is talking about acceleration, and there are forces involved, therefore this is a Newton's second law problem. F net equals mass times acceleration. Alright, so let's get busy. I'm going to label these two boxes just so that I can tell them apart in my diagrams. The box hanging will be M1, the box on the table will be M2. I need to know all the forces acting on that box, and the best way to find that out is a free body diagram. Mass 1 has its weight, the force of gravity acting on it, force of gravity for box 1, and it has a tension. Mass 2 has gravity acting on it, its weight. It has a normal force. If it's going to move to the left, see the diagram says velocity to the left, it has a force of friction to the right, and it has tension to the left. Tensions are the same. There's only one string, so there's only one tension. The problem tells me my acceleration, A equals 5 meters per second squared. So this problem is looking easier and easier because we already know a lot of the information for it. We now need to deal with the net force for each box in order to find the force of friction. The net force on box 1 will equal mass 1 times the acceleration, which we already know to be 5 meters per second squared. There are two forces acting on that box, and they are both in y, so this equation could easily say F net y equals mass times acceleration in y. Tension is pointed up, and let's call that positive since up is positive. Weight is pointed down, we'll call that negative, equals mass 1 times the acceleration. The accelerations on these boxes are the same, so I'm not going to differentiate the acceleration by putting 1 or 2 or x or y. We already know the accelerations, and we know they're the same. Now let's look back at box 2, F net 2, and this box is going to move in x, not in y. Clearly from the diagram, that box is not going to fly up or fall down. So F net 2x equals mass 2 times acceleration in x. Okay, the forces acting on that box are tension to the left and friction to the right. Now we typically call right positive and left negative. But to make this problem slightly easier, let's change up our axes. Let's continue to call up positive y, but let's call left in this problem positive x. You could continue to say that all left forces are negative and right forces are positive and get the same answer I do here. But because I know that box is going to move to the left, I'm just calling the direction of motion positive, and that's completely allowed. You get to declare your coordinate system. You just have to tell the people on the AP test which way is positive x, which way is positive y, so that they don't assume you just put in numbers randomly. So I'm telling the AP people by drawing this diagram, up is positive y, left is positive x. Something I notice if I'm going to follow that convention, my box 1 is falling down. Therefore, its acceleration must be negative, making this whole term on the right of the equation negative. Just like gravity being negative, we usually go ahead and put the negative in. The box is falling down, therefore its acceleration is negative, and this term right here becomes negative. Alright, back to box 2. Box 2 has acting on it a tension, and we just defined left to be positive x, so there's our tension. It also has a frictional force acting to the right, which we've called negative. T minus friction equals mass 2 times the acceleration. And again, I'm not differentiating the accelerations. We know them. We know they're the same. So now we've got to solve for the force of friction, because that's the thing we have to know before we can answer the question. I need to use both of these equations because I currently have two unknowns. I have tension and force of friction. I don't need to know the tension, therefore, why don't we work to eliminate it using our algebra skills? I'm going to solve this equation over here on the left for tension, and then whatever I get, I'll substitute in for the tension here on the right. Let's go. Solving for tension, I add force of gravity to both sides. Tension equals Fg minus m1a, because we decided this term is negative due to the fact that the box is falling. Now I'll take that tension I just found and put it into the equation over here. Therefore, Fg minus m1a, which was just tension, minus the force of friction equals m2a. And before anybody gets confused, let's just remind ourselves that this Fg is the Fg from box 1. This term in parentheses here is simply the tension from above, substituting the tension I found from box 1's equations into box 2's equation. Now we need to solve for the force of friction. So why don't I add friction to both sides and subtract m2a? That way the equation becomes Fg1 minus m1a minus m2a equals the force of friction. Now I'll plug in my numbers. Fg1, that's a 1 kilogram mass, meaning its weight is 10 newtons, minus the mass of that box, 1 kilogram, times the acceleration of that box, which the problem tells us is 5 meters per second squared, minus the mass of box 2, 0.5 kilograms, times the acceleration, 5 meters per second squared, and all of that equals the force of friction. So grab a calculator, try that out. I'm going to do the same, and let's see what we get. I found the force of friction to be 2.5 newtons. And just to review how I got that super fast, 10 newtons minus 1 kilogram times 5 meters per second squared. This whole term here would be 5 newtons. 0.5 kilograms times 5 meters per second squared, this would be 2.5 newtons. 5 newtons minus 2.5 newtons gives me 2.5 newtons. So now we're just looking for the coefficient of friction. We know FF, we know the normal force. I'm going to take this to another slide and clean it up a bit. Okay, here's the information we have from the last slide. We're using the equation force of friction equals mu k times the normal force. The force of friction is 2.5 newtons, the normal force is 5 newtons. Let's solve the equation for mu k and then plug in our numbers. FF equals mu k times the normal force. Therefore, mu k, if I divide by the normal force on both sides, equals FF divided by the normal force. Okay, now let's plug in numbers. Mu k equals 2.5 newtons over 5 newtons equals 0.5, and that's mu k. There are no units on a coefficient. We have found the coefficient of kinetic friction. If you're confused, I split this night up into multiple videos so that you can rewatch any parts you're confused about. So if this confused you, please rewatch it again. That's all. See you tomorrow.